Okay, thanks very much, Steve, for this nice introduction. I'm now going to turn off the lights, which is better for the filming. Is that okay with everyone? It also, you can see the slides better. You can't see me as well, but I don't think that matters. So let me talk I'm going to tell you about the Higgs boson at the Large Hadron Collider. This here is what we call it an event display. It's a graphical display of one of the events that we recorded last year in the ATLAS experiment at the LHC, and this may or may not be actually a Higgs boson. So, in fact, when I was first asked to give this talk, I was going to give a general talk, but mid-December, there were a lot of news stories, in fact, about the Large Hadron Collider, and here you see some from the BBC, which said that the LHC, the Higgs boson may have been glimpsed. And the New York Times said data hints at elusive particles, but the wait continues. So I'm going to tell you what this is all about, about these tentative hints for the Higgs boson that we may have seen last year. So the outline is that I'll first talk about the Large Hadron Collider, what it is, how it works, and what its experiments are and how those work. I will then tell you about the particle physics in general, what are the current successes of particle physics, and what are the remaining mysteries. And in particular, I'll focus here on the mystery, what is the origin of mass, which the Higgs boson is explaining. And then I will tell you about the first results from the Higgs on the search for the Higgs boson before I conclude. Okay, so this is an aerial view here of the Large Hadron Collider. It's located at the outskirts of Geneva, at the Swiss-French border, in fact. It has a circumference of 16.5 miles. It's this red ring here. And you see, for instance, here in the back, there is Mont Blanc, the highest mountain in Europe, which you can, in fact, see from the cafeteria at CERN, which is the laboratory, the European Laboratory for Particle Physics. Then you see here these yellow dots. These are then the four experiments. So what happens at the Large Hadron Collider, you have protons colliding with each other in these 4 points. So one set of proton goes this way around, the other one goes counterclockwise, and then they are brought to collisions at these 4 interaction points, and which we have equipped then with large, what we call detectors, with large detectors. The one that I'm actually working on, and we have a large effort here in Berkeley on this, we have about a group of 45 people working here on the ATLAS experiment. And then the other experiment, which does very similar science, it's actually identical science to the ATLAS experiment, is on the opposite side, the CMS experiment, and I'll talk about those two. The other ones, called ALICE and LHCb, they are geared also at particle physics, but at different aspects of it, and I'll not talk about them. They don't do anything related to the Higgs boson, basically. LHCb is trying to understand antimatter, and ALICE is trying to understand very hot conditions in the early universe. So it's also very interesting. Just to give you a feel how big the LHC is, so I've transported it here into the bay, so it has a diameter approximately of the Bay Bridge. And remember, so the protons go around, one set goes clockwise, the other counterclockwise, and they go very, very fast. They're going at 99.999999% of the speed of light. And how fast that really is, what they do is they make a full turn around this ring 11,254 times a second, okay? And there's a lot of protons there. So in fact, we put them into bunches, these protons, and there are 100 billion protons in each bunch, and we have 1,000 bunches. So there's a lot of protons there. So how does the accelerator then actually work? So we so protons are, so we are trying to get them to be at very high energy. And in order to do that, this is how, some of you, I think, might remember how TVs worked before they became all digital, or plasma TVs don't work like this, but TVs like in the 90s or 80s worked like this, that you have a radio frequency. Every time a proton passes, this radio frequency, energy from the radio wave is transmitted to the beam, giving them a little bit of a kick. So they get just a little bit of a kick every time. They pass around many, many times, and that way they get more and more energy. And then they get more and more energy. Now, this is a picture of one of these devices. If they get more and more energy, then what protons like to do, normally they go just straight. So they just fly on straight forever. This we don't want. We have a circular machine, so we need them to go in a circle. And this we do via magnets. It's via the Lorentz force that we apply a magnetic field, and that way we can make them go around in circles. And these are very large magnets. So this is the Director General of CERN proudly presenting one of these large magnets. Yes? Sorry? Okay. 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 Okay, no problem. Thanks. Okay. Now, accelerators were actually first developed here in Berkeley. In fact, Ernest Lawrence, who was a faculty member in the physics department here in the 30s, he won the Nobel Prize in 1939 for the development of the first accelerator ever. And this is called the 5-inch cyclotron. The reason that it's called the 5-inch cyclotron is that it has a size of 5 inches, and it's displayed here at the left. The energy, and I'll explain these units in a moment, the energy that this 5-inch cyclotron reached was 80 kiloelectron volts. The LHC accelerator has an energy, reaches an energy 80 million times larger than that of Lorenz's cyclotron. It is a vast scale. You see here again the magnets. Here you actually see one of these. So there's 1,000 magnets of these, 1,200. And this is when the last magnet was lowered into the LHC ring, which is also 300 feet underground, through these shafts, was lowered into the accelerator ring. The cost of it is, of course, also substantial. It's $8 billion. So the best way of explaining everything is to have a movie. So I'm having a movie now, which I hope works. Okay, so here we have a proton. So they start off at very low energy and then become into pre-accelerators. The booster, this is the so-called proton synchrotron. Then they go into the super proton synchrotron. You see these two bunches of protons going around, and now they're in the LHC. And so they're circulating, and then we are now diving into the LHC. Here you see an interesting formula, which I'll explain later. So we're going like this is the French-Swiss border you just saw. So this is a proton. It's a very dynamic object, which they tried to illustrate here, which has quarks inside. So now the proton here, one coming from the right, one coming from the left. Now this is the Atlas detector, and now they collide. And when they collide, then a lot of new particles get produced. And this is what you see here. And this is the essence of what we're trying to do. So a lot of new particles get produced, and we're trying to understand exactly what are these particles, to measure all the energies, everything about these particles that got produced, okay? So, and the particle that we're most interesting, and which particle gets produced is not predictable. Sometimes a Higgs boson can get produced, but much more often less interesting particles get produced. It's just purely a probabilistic thing. Whenever two protons collide, there is a probability that a Higgs boson comes out. There is a probability that other standard model particles come out. So we try to record all of them where we have some logic to filter out the most interesting events when we are already online when we're recording. So this is a slightly boring thing, but it's very important. So because so what we're going to talk about for the rest of the talk is mostly mass, but we don't really measure mass in kilograms or pounds or any of those units, but we use them as the unit of electron volt over c squared, where c is the speed of light. So I wanted to explain to you what that is. So 1 electron volt is equals to 10 to the minus 36 kilograms. So 36 zeros, 18. The particles that we're going to talk about, so protons are being accelerated in the LHC, so the mass of a proton is 1 giga-electron volt, which corresponds then to 2 times 10 to the minus 27 kilograms. The electron, for instance, which I think you're all familiar with, has a factor 1,000 smaller mass approximately. Just to set the scale, I also just put here the mass of the sun. That's 2 times 10 to the 30 kilograms. So basically the mass of a kilogram with respect to the sun is a very similar relationship to that of the mass of the electron. And the Higgs boson, which we'll talk about, of course, this has a mass which is about, which we don't know, as I'll say, but it should be in the range between 100 and 600 giga-electron volts. So it's about 100 to 600 times the proton mass. And this, of course, then again translates to of the order of 10 to the minus 25 kilograms. So when I talk about a heavy particle, this is very relative. I consider the Higgs boson to be a heavy particle, but of course, in terms of the masses that we physically deal with in daily lives, it's a very tiny mass. But it's heavy compared to, for instance, the electron or the proton. So the unit that I will mostly use is giga-electron volt. I try to always say it's equivalent to the proton mass, but sometimes I might slip into slang. So just remember, a giga-electron volt is just equals to the mass of the proton. And so at the LHC, we are trying to create very high energies. Or we are also succeeding with that. We are creating very high energies. And here I want to explain why this is actually important. So it really comes just down to Einstein's famous formula, E equals mc squared, that energy, it says that energy and mass are equivalent. Here c is the speed of light, m is the mass of the particle, and E is the energy. So what we're doing is we're colliding 2 protons with an energy of 3,500 giga-electron volt. So 3,500 times the proton mass. So then the total energy is just the sum of the 2 protons is 7,000. By having this energy, this allows us to create any particles that have a mass up to 7,000 giga-electron volts, yeah? Because the way it works in such a collision is pictured here. So here we have the 2 protons. Protons are composite objects. They are not fundamental, so they don't directly interact with each other, but the constituents of the protons, which are called quarks, they interact with each other, and then they can create a new particle, which I just call X here. Could be Higgs boson, could be something else, okay? They created a new particle called X. So the mass of this particle X can at the very maximum be 7,000 giga-electron volts at the current LHC. At the previous collider that I worked on near Chicago, this was 2,000. And for instance, there were colliders, of course, also in the 80s and 90s where it was order of 100, yeah? And not only that, also the higher the overall energy, even if the particle mass is smaller than 7,000 giga-electrons, it's better to have more energy because we have then a bigger flux of these quarks. So the higher the energy, also even for lower energy particles, we gain the higher the energy of our accelerator. Now then what happens is we have this new particle called X here created. Nearly all the new particles that we're looking for are extremely short-lived. They live really a very short fraction of a second only, and then they decay immediately into known particles. So this is illustrated here in this graph, that this particle X here decayed into an electron and an anti-electron. And so we never observe this particle directly. We observe what we call the decay products, here the electron and anti-electron, and by measuring the energies and angles of these particles very precisely, we can work out the properties of this particle X. Okay, so then let me tell you about our theoretical model, which we call the standard model. Not a very exciting name, but that's what we call it. I already alluded partially to this. So in the last century, we've really made a huge amount of progress. In about 1900, it was still thought that the atom was the smallest particle that there is. That's what the word atom means. The Greeks came up with that. And since the Greeks, so since like, since the year 0, until about 1910, it was actually really the atom was considered to be the most fundamental unsplittable particle. But then in 1910, Sir Ernest Rutherford made an experiment and worked out that indeed the atom is not a fundamental particle, but it consists of a hard core, which is the nucleus, and electrons whizzing around that, okay? And here, so the size that of this nucleus is about 10 to the minus 12 centimeters. And then later in the 40s, it was also realized at that moment then that the nucleus was not a fundamental particle either, but it consisted of protons and neutrons. So this was, which are about a factor 10 smaller than the nucleus itself. Then the story continued in 1969, actually. It was then realized that the proton and neutron are not fundamental particles either. They yet again consist of smaller particles inside them, and these are known as quarks. And this is still the state of the art today. So at this moment, we know that all matter in the universe is made up of quarks and electrons, pretty much. Now, what we're doing at the LHC, we're now going, so you see we have a less than sign. So we don't really know how small the quark is. We don't really know how small the electron is. All we know that it is for sure smaller than 10 to the minus 16 centimeters. It could be 10 to the minus 17. It could be 10 to the minus 35. This we don't know, okay? At the LHC, we're now going down by 1 order of magnitude to 10 to the minus 17 centimeter and trying to probe that. So what do we know now? So what does our theory now tell us? So on the left-hand side, you see all the particles, all the fundamental particles that we know of to date and that are incorporated in our best theoretical model. So we have in orange and green, we have so-called quarks and leptons. I already explained to you the quarks are the constituents of the proton. But there are, so the ones that are in the proton are only the ones labeled U and D, which are so-called up and down. But there is a total of 6 quarks. Also charm, strange, top and bottom, they're called. So in our normal world, the other 4 don't play any role. They don't actually appear on Earth. Well, the up and down quarks are all over us, all inside us, but the other 4 don't matter at all. The last one was discovered, the top quark was discovered actually here at this accelerator in Chicago in 1995. Then the other type of particles, which are the leptons, and the one that you know is the electron, which whizzes about the nucleus in the atom. But again, that's not the only one. There is also a total of 6 particles. In fact, muons, so the second particle there, the mu, Greek mu, that is a muon, and these get frequently produced in the sun and actually hit us here all the time, but they don't do anything. You don't realize this. But anyway, the Earth, everything we see on Earth is basically only those three so particles from this first generation, we call it, which is on the very left. In fact, when the muon was discovered, and that was a long time ago, it was in the 40s, Isidore Rabi, who was a famous physicist, said, who ordered that? And this is still an open question, and why there are so many copies, why there are 3 copies. The only difference between these 3 copies is the mass. They all have different masses, and going from left to right, they get heavier and heavier. Okay, anyway, so these are matter particles. Now, the other kind of particles that we have are force carrier particles. So these are there in purple. One of the forces is the electromagnetic force that, of course, you all know. So this is carried by the photon. Another force is carried by the gluon. That's the little g. That is the strong force. That force you don't experience in daily life, but that is the force that holds these quarks together inside the proton. It's a very strong force that binds them. So, for instance, the up quarks, they all have the same charge. We have 2 up quarks and 1 down quark in the proton. The 2 up quarks would repel each other in terms of the electromagnetic force because they have the same charge. But the strong force is much stronger than the electromagnetic force and can hold them together anyway. And the last but not least, we also have the weak force, which is carried by these, the W and the Z boson. And this is, without that, the sun wouldn't burn at all, and nothing would work, of course. So all of these particles are very well known. They've been studied a lot at previous colliders. Now, there is one particle in the very middle, which is the gray one, the Higgs boson, and it's also known as the keystone of the Standard Model. Because the role of the Higgs boson is to give all the other particles mass. I already told you, so without the Higgs boson, none of these particles would have mass, which A is completely against experimental observation. All of us have mass, so if there are no fundamental particles have mass, this wouldn't work. And second of all, even having the different copies, we know they have different mass. So we need a mechanism that generates mass for them. And this is hypothesized to be the Higgs boson. But that is, out of all the particles that I show you there, that's the only particle that hasn't been observed yet. Yes? I'll explain in a second. Just before I do that, let me just explain this theory that we have is an excellent theory, apart from the fact that we haven't observed the Higgs boson yet, but that's really not the fault of the theory either. So it's a very, very precise theory, and it teaches us how to calculate any process that involves any of the fundamental particles that we have. So I'm just giving you here a flavor. So actually, Richard Feynman, who was at Caltech, pioneered this at the time. So for instance, here on the left, I'm showing you a process where we have an electron and an anti-electron colliding, making a Z boson, and that decays into 2 quarks. And what I'm showing you, so this is the total energy here, what I'm showing you is the different points. These are all measurements made in the last century, and the black line is the theoretical prediction. So you see how excellent the agreement is between all these data measurements and the theoretical prediction. Theoretical prediction is really precise. In this case, at the level of 1%, it can accurately predict what we should be measuring. And this was tested in many experiments. The different colors are different experiments, basically. Similarly, this is a different process. Here we have a quark and an anti-quark. Whenever there is a bar, it means an antiparticle. It's antimatter. They make a gluon, and that goes again to a quark and an anti-quark. And again, you see the data here is the black points, and the red circles are the theoretical prediction. Again, they're an excellent agreement. In these processes, the precision which we can do this. Whenever there is quarks in the initial state, it's a bit harder, but we still can predict this at the level of 10% or so, what should happen. But, of course, we're not happy with, I mean, so it's a very good theory. It lets us calculate all of this, but it lacks giving answers. I mean, so it doesn't provide answers to quite a few very fundamental questions. So why do particles have mass? It provides an answer, but it's experimentally not verified yet, and this will be the topic of this talk, of course. There's also many other things that I will not have time to talk about today, but for instance, what is dark matter? We know that there is a factor of 5 more dark matter in the universe than there is visible matter. All the particles I described only make up the visible matter, so there are many theories that can explain what the dark matter could be, but again, there's no experimental evidence yet. For all I'm talking about, gravity does not actually matter at all because it's a very, very weak force, and we do not yet understand why gravity is so much weaker than the other forces. There are very interesting theoretical explanations related to string theory. For instance, that there's extra dimensions. And also, for instance, where has all the antimatter gone? Our theory would predict that there is approximately equivalent amounts of matter and antimatter in the universe, but that's clearly not correct. So we're still looking for a mechanism, a physics mechanism that makes all the antimatter disappear. But I'll focus here on just the first question. Maybe you can persuade Steve to invite somebody to cover the other interesting questions. Okay. So what is this Higgs boson now? So really, there's 2 things. So first of all, in fact, the first speculation was just to introduce a new field, which is called the Higgs field. In particle physics, we identify very often a field with a fundamental particle. So the photon, for instance, it takes care of the electric field. So this field was introduced actually in 1964. This idea was, quite a few people have had it in parallel, so different groups. So on one hand, Peter Higgs, who is this guy over here. Then there's 2 guys in Belgium, Englert and Brout, and then also Goralnik, Hagen, and Kibble. All came up with very much this idea in 1964, and the mathematical expression is there, the top line here. This doesn't necessarily explain to you exactly what the Higgs boson is, so I'll try to explain it in a more qualitative way. So really, it's a field that permeates the universe. I don't know if any of you have heard of the ether, which was a very hot topic at the end of the 19th century and was ultimately solved by special relativity by Einstein, that there is no ether. In some sense, the Higgs is actually not that different to it. So we just imagine that there is a field in the universe that causes particles to slow down. So on the left-hand side, this is when there is nothing in the universe, no extra field. So then all particles just go at the speed of light, undisturbed. They just go. On the right-hand side, this is how a Higgs field would act. So, or you could imagine it as a fluid, so that basically it makes these particles go, it interacts with them, and that way slows them down, so they don't go on a straight path anymore, but they get slowed down, and because they get bounced around by this field, and so then they go much slower. And going slower is exactly equivalent to saying it has mass. So in this case, for instance, the photon doesn't have any mass. It has a mass of 0. So the Higgs field has no impact at all on how photons move. However, the electron, which has a small mass, so it has some impact on that, but not very much, but a little bit. So wherever there is a red cross, that means that the Higgs field interacts with the electron, and so it slows it down. The top quark, which is the heaviest particle we know so far, interacts very, very strongly with the Higgs boson, and so it gets slowed down very, very much. And so what the Higgs field really does, it just slows down these particles, but that is exactly equivalent to meaning that they get mass. There is a more qualitative explanation of it, which was thought of by David Miller from UCL, which was the UK government challenged the scientists to explain to them what the Higgs boson was, because they were asking for funding to find it. So the way David Miller explains it, which is very nice, is that imagine you have a party and all guests are kind of chatting with each other. None of the guests is more interesting than any other, so they just chat randomly to each other. This is there on the left. But then if you have a celebrity arriving, in this case Margaret Thatcher, there's a movie out right now, I think, which I haven't seen yet. Anyway, so Margaret Thatcher, then of course everyone gets excited, but it could be Barack Obama just as well, maybe even more exciting actually. Anyway, so then the guests of course get excited and they all want to talk to that celebrity. And so all they basically move there, and the celebrity cannot move freely in the room, yeah? The celebrity must move much slower because there's all these people around her. Then a boring guest can just walk through, nobody cares, okay? So basically in this case, Margaret Thatcher is much more massive than a boring guest. Yeah, so then the other step is, so this is just the Higgs field itself. The question is to identify now, once we have a field, whether this is related to a fundamental particle. So generally, this often is the case. So for instance, the electric field is related to is identified with a photon particle. The strong interaction field is identified with a gluon particle. But however, in the initial paper that Peter Higgs wrote, in fact, he did not identify this field. He only talked about the field. He did not mention that this could be a new fundamental particle. However, it was, in fact, this paper was initially rejected by the peer review of this journal that he submitted it to. And then he added this sentence, it could be a new fundamental particle. And that the journal then was persuaded that this was exciting enough, so they published it, yeah? So this is not necessarily the case, and in fact, it's quite possible that the Higgs field is not represented by an elementary particle, but by some composite object, like, for instance, a proton. I mean, it wouldn't be the proton, but just in the spirit that it's a composite object. And this is, in fact, one of the big questions we're trying to find out at the LHC, whether it is a fundamental particle or whether it is just a field consisting of other fundamental particles. So what do we know about the Higgs boson? So we know that it's supposed to give mass to particles, and we know a lot about it mathematically. We use it in our calculations. However, what we don't know at all is what its mass is. Well, we don't know if it exists either, but we also don't know if it exists, what its mass is. There are some reasons, so I'm showing you here some graphs which are narrowing the Higgs boson mass range. So on the left-hand side, you see everything in the green band, basically. So the left axis is the mass of the Higgs boson, and the green area is what's allowed. This is just from purely theoretical arguments requiring that the universe would have been stable at least between its creation and now. If it's not in the green or yellow, it wouldn't have been stable until now. Actually, if it's in the green, it's stable forever, and the yellow, it means it may collapse very soon. And so basically, it prefers to be in a range where it's at all energies it works. It's around 200 gigaelectron volts. And this is another plot which is quite complex, but from indirect measurements, we also know that we think that it should be between 100 and 160 gigaelectron volts approximately. Okay. So this is what we're looking for. We're looking for a Higgs boson between around 100 and 200 gigaelectron volts, although as an experimentalist, even if the theorists prefer such value, we of course look for it everywhere, just in case, you never know. So the main ways that we're looking for the Higgs boson are depicted here. So this is the diagram. This is where I spent some time earlier introducing such a diagram. These are quite complex. So on the left-hand side, we have two protons interacting via gluons. These are these Gs, making a Higgs boson. And then in this case, the Higgs boson decays to 2 photons. On the right-hand side, so this happens actually 0.2% of the times when a Higgs boson gets produced. 0.2% of the time it will decay into 2 photons. 1% of the time it will decay into 2 Z bosons. Z bosons are again not stable because, so the Higgs is unstable. It will decay immediately to 2 photons or 2 Z bosons. The Z bosons in turn are not stable either. They in turn decay again, for instance, into an electron and an anti-electron, a positron here, or muons. So 7% of the Z bosons decay into electrons or muons. So 99, and these are the ones that I'm going to talk about. So I'm only going to talk about 1% of the Higgs bosons that decay in these ways. 99% they decay also into other particles, but this is much harder to observe. And so these 1% are really the precious 1% of the Higgs bosons that we can do something with. The other 90% are much harder to identify, and we also partially use, but they are nowhere near as powerful as these two. And so, as I told you, we have a very precise theory that can tell us exactly how many Higgs bosons we should observe, for instance. So we can, once we just assume a given Higgs boson mass, we can fully calculate how many Higgs bosons we should observe. We can calculate how often it decays to a photon, to 2 photons, or 2 Z bosons. And the precision of these calculations is about 15%. So, for instance, in the data we've taken so far for a Higgs boson mass of 120 gigaelectron volts, we expect there to be 70 events where the Higgs boson has decayed into 2 photons, and 1.6 events where the Higgs boson has decayed to 2 Z bosons, which both decay to leptons. So now, okay, so 70 is certainly a good number that we can try to. Now we need to find these 70 Higgs bosons, yeah? This is really in a year. This is 1 year. Ah, yeah. Yes, sorry, I forgot to say that. That's a good question, yes. Yes, this is in all of 2011. So we have to now dig them out of the rubble, and this is what I'm coming. So we have to find these 70 events in a year's full of data. And this is, on the left, this is basically what we observe in our experiments, and we're trying to figure out whether that's related to this process here on the right, yeah? So to explain how we do that, yeah?
You showed the quarks, so an anti-quark is a quark.
Oh, here? Yes, this is wrong. This should be both protons. Yes, this is at the Tevatron accelerator. We had proton and antiproton. So yeah. It doesn't matter much, actually, honestly, because in both you have quarks in there. Okay, so now we need to identify these Higgs bosons, and for this we build very large detectors. So this shows, and the basic principle of them is that they have an onion-type structure. We have different detector technologies that we use, and they are aligned in a concentric way around the actual collision, as you already saw in the graphics, actually. So here, so the proton collision happens here in the very middle of this white circle, and then new particles come out, and these could be any kind of particles. So for instance, an electron, and in electron you see here this red thing, this is what we call our calorimeter. We observe a shower of particles here, and in this, I don't know what color that is, bluish thing, this is a tracker, what we call tracker, which is able to observe charged particles but cannot see neutral particles. So just the pure fact that there is something here tells us that this is a charged particle which is very electromagnetic, and that's an electron. For instance, at the top you see a photon. it behaves in the identical way in the red part, which is our calorimeter, because it's also an electromagnetic particle, but it doesn't have any charged particle track pointing towards it because it has no charge. The photon has no charge. And then we have, for instance, a muon, which is not, so these particles here get stuck in this red calorimeter. There's nothing behind it. The muon doesn't. It couldn't care less about this calorimeter. It just flies through all the way into the blue detector, and that way we realize that this is a muon. This is the basic concept, that we build this cylindric layout, and different particle species are observed in a different manner in our different detector layers, and this lets us tell muons, electrons, photons, protons, etc. apart from each other. Not only that, actually, we can also measure then the energy and all the angles of these particles. And these are the large detectors that we've built for this. This is the Atlas and the CMS detector on the right, Atlas on the left. These are they weigh about 10 kilotons and are also really large. They are 40 or 20 meters long and have a height of 22 meters. So this is about the height of LeConte Hall, which is just adjacent here to Evans Hall, not quite the size of Evans Hall. They're also very heavy. So just to illustrate this here, so CMS detector is actually 30% heavier than the Eiffel Tower, because it's made of, a large portion of it is made of lead crystals, and lead is very heavy. These are pictures here of these detectors, so these are of the tracking detectors. So for instance, the detector that is most close to my heart is this one. It's the pixel detector, and this was largely, we designed this and even built parts of this here in Berkeley and then shipped these parts to CERN. It's a detector which is the size of, it's about 1.5 meters long. It's like this long. It has a diameter like this. It directly surrounds the beam pipe. And here you see us, for instance, assembling it here. This is the detector here at the end. And these are many of our grad students and engineers and scientists here from Berkeley that were involved in doing that. This was in 2007. Yeah, this is a calorimeter. So this is what we use to identify electrons or photons. When they deposit energy, we measure an electromagnetic shower and measure the energy of these particles. And these are the very large, they dominate the size of the experiments, the large muon detectors you see here in the Atlas cavern. Here, the CMS, the red thing is the muon spectrometer here. This is Atlas. These are all muon chambers. So these are large. And they're at the very outskirt of the experiment. The experiment then, given its size, it also needs a lot of people working on it. So we have 3,000 physicists from all over the world. You see here a map of the countries involved. So obviously the US there on the left, but you see also, for instance, we have Africa, we have Australia, we have South America, and then, of course, Europe a lot, etc. And we have many PhD students, of course, who are working on this. Okay, so this is basically the prelude. Now come the actual results. So the LHC was, in fact, was already thought of in the mid-'80s. This was the first time when people were thinking of building such a machine. There was also one in the US, which later was killed by Congress, but the LHC has survived. And it really the construction really started in 2000, and it was finished in 2007. So this was when the last magnet got installed in the LHC. It's really a project of several generations. In then 2008, and maybe some of you have heard this in the press, there was a lot of media attention at the time, was when the first protons were ever circulated in the LHC. However, shortly afterwards, there was a major accident which then prevented LHC to start that year, and there was basically a year delay to really start. So in November 2009, we really finally had the first proton-proton collisions, at a lower energy still, and in March 2010, the first collisions at the energy that we cared about. Then last year we recorded a data set which is in units, well, a small data set, let's say. 40 inverse picobarn, this is called, but it doesn't matter so much the number. It's a small data set with which we could understand a lot of the standard model mundane processes that have been calculated before. We could measure them, we could check if there's anything interesting. We could also test some new physics models, for instance, supersymmetry, which is related to dark matter beyond the tevatron, but we did not have enough at all to look at the Higgs boson. So last year we would have had only 0.7 Higgs boson events in the diphoton. I told you 2011 we had like 70, the year before it was 0.7. So okay, then you can be lucky there's 1 or there is 0, so what can you do? So, yes? Oh, so that is the accelerator that we had at Chicago. And so now this year, this is 100 times more data than, well, so it's already last year. So in 2011, we recorded then 100 times more data than the previous year. And so this is then now sufficient to actually look at the Higgs boson properly. And there was a lot of happiness when it turned on. So this is in our control room here. The person in the purple shirt, she's our spokesperson. Person left to that is the main scientist to conceive, who made the LHC work in the first place. And there's a lot of excited people there because it has been a long wait until it finally worked, of course. So I'd already mentioned this unit inverse femtobarn. So why is this important? This is what we call luminosity. Luminosity is just really how many proton-proton interactions there are. So this 5 inverse femtobarn of luminosity, and this is just showing here how this accumulated during the last year. We're doing a 24/7 operation, and then whenever we operate, we increase the luminosity. And so you see that it basically steadily increased. There are some flat regions, so this is when there is a maintenance of like 5 or 6 days, which is quite typical, which you see every 6 weeks or something like this, yeah? And this luminosity, it just measures how many proton-proton interactions there are. And in fact, this number of 5.5 means that we've had 4 times 10 to the 20 proton-proton interactions, okay? And 70 of those may have been the Higgs, okay? So we have to filter these 70 out of these 4 times 10 to the 20. That's my job. Now, when we record the events, so this shows one event that we know very, very well. So this is the Z boson, Z boson, which was already discovered in 1983. And so this is how it looks in our detector. It decays. So this is the diagram. We have a quark and an antiquark making a Z boson and then decaying to 2 electrons. So the collision was here in the very middle. These yellow tracks are then the trajectories of these electron and positron. And here, this yellow blob, that corresponds to that there was a high energy measured in our electromagnetic calorimeter. The chance that this actually is a Z boson, this is very small background. There's virtually no events that look like this other than this. So the chance that this actually is a Z boson event is about 99%. We can never be 100% sure with any event exactly what it is, because there can be other ones that look very similar. And this is much worse for the Higgs boson. So the Higgs boson, as I said, so we're now going to look for the Higgs boson decaying to 2 photons. This is this diagram there at the top. But there is processes that make 2 photons that have nothing to do with the Higgs boson. So some process that could occur is this one, where we also get 2 photons just like there, yeah? So this, just observing 2 photons is not good enough to know that it's the Higgs boson, because it could just be that process. And what is worse is that the rate at which this happens is about 50 times larger than the rate at which the Higgs boson occurs. So instead of 70 events, we have like 2,500 of these. Okay? So what do we do? So what we do is that we can actually, by measuring these angles and the energies and momenta of these particles precisely, we can actually calculate what is the mass of the particle they came from. So for the Higgs boson, since they came from the Higgs, this should be at the mass of this Higgs boson. While here, there is no actual particle they came from directly. They just got radiated off of quarks, and so they're not associated with any given preferred mass value. This can happen at any random value of the mass, and this is shown here. So this shows the mass distribution. The yellow is this background, and the red is the Higgs. So if we construct this quantity, the red are all accumulated here, in this case, at 130, while the other ones have a smooth distribution. And so this is exactly what we're looking for. We're looking for a little peak on a big, smooth spectrum. Note that, but this peak is very small, so this is 0. So there's about 5,000 yellow events in this case, and like 100 red events. So we need to look for these. And of course, in our experiment, they are not painted red. So, so this is one event that has such a feature. So it has these two photons. So it looks very similar to the Z event that I showed you. You have these two photons. But in this case, we don't have a charged particle track pointing to them. So this is why we think these are photons. But we don't know whether they came from Higgs or whether they came from that. But I told you that the ratio is about 1 to 50. So in this case, the chances that this really is a Higgs boson is at best 2%. Okay? Well, for this, yeah. So we can't, again, decide this on an event-by-event basis, but we make this plot of this diphoton mass distribution. And this shows now the real ATLAS data, or the data we took last year. And this is where we're looking for the 70 events. So the black points show the data. The red shows our background model. So that is what was yellow on the previous plot. So this shows a smooth distribution. And the dashed red shows how a standard model Higgs boson, for instance, would look like if it had a mass of 120 GeV. So now, the interesting thing why there was a lot of attention in the media is in the center of the plot at around 125. You see that there are a couple of bins here. Here. So the data points, the black points, and this is the error bar on them. So whenever the data are basically in agreement within this error bar with the red, this means it looks like background at that position. However, here you see that they are further away than the error bar indicates, and this one and this one and this one is just at the edge. And so this is exactly, in principle, this is what we would expect from the Higgs boson, how it would show up. That we have 2 or 3 bins that deviate from the red line, okay? But this is just the data from one experiment. Now, the great thing is we have 2 experiments, so either one experiment can have made a mistake, or anyway, we are also doubling the data looking at the other one, so we can look what the others see. So this is shown here. So the left is just what I already showed you. This is here on the right, and this is this region. So it's very hard to say. There is also there's also, again, one bin here which is a little high, but then there is one next to it which is a bit low. So it's not conclusive, yeah? It's not conclusive. This is why there is a lot of excitement, but it's not conclusive. Then they can also, as I said, decay into 2 Z bosons. So this is shown here, and again, this is very different. It's much better in terms of the signal to background. So here we have a signal to background of about 1. This is what we should be seeing. So the black is now the background, and these dashed lines are hypothetical peaks at different Higgs boson masses. So you see that now we're looking basically for about 2.5 events. 2 events depends on the mass a little bit on a background of about 1.7. So here, when we see an event, it has about a 50% chance then to be a Higgs boson. And this is how, and again, we're looking at this mass distribution. So I just circled here what's happening at this value at around 125, where we see something in the photons. So you see there are some events here also. There's like 2 in CMS. There's 3 in Atlas. Again, the error bar indicates, I mean, so when you have 2 or 3 events, the error bar is very large. So it's not conclusive, but it is certainly interesting. There's no other peaks in the data distribution. You see here some hypothetical peaks, how a Higgs boson would look like. That's the pink here on the left, for instance, and the yellow and the light blue. This is what we would expect if we had high statistics, but this we don't see. And so this is an event. This is the ZZ boson event. Okay, and this is the money plot. Unfortunately, the money plot is a very complicated plot to explain. But here, what we do is so if we don't see something, it doesn't mean that we are just depressed and go home. We actually still get scientific information out of that, because we know that we can see it if the rate is high enough. So if we don't see it, we can constrain the rate. We can say, well, the rate of these must be lower than some value, yeah? And this is what we do. So so the black line, so what is basically shown here is the rate of Higgs bosons we exclude divided by Higgs bosons predicted by our standard model theory. So the black line, it means that any rate above the black line is excluded. And red means it's the standard model. So what it means is that we are excluding, whenever the black dips below the red, that means we've excluded the standard model Higgs boson at that mass value. And in fact, you see that this is true for the entire mass range up to which is sort of in this yellow hatched region. So from 127 on the left up to 600 giga-electron volts on the right, we've wiped out that entire Higgs mass range. So it definitely can't be in that range. It can still be. There is only one window left where it's still allowed to be, which is here, and which is between 114 and 127. That's the only place left. And in fact, the tantalizing hints we're seeing at 125, which is in this allowed range. Now, we have not 100% excluded this mass range. We're excluding it with a probability of 95%. And so the reason that since we see a little more events, both experiments see a little more than we would expect if there wasn't a Higgs boson at 125, we see here these little peaks in both experiments at Atlas and CMS at around 125, where we can't exclude the Higgs boson because maybe we are starting to see it. But we can't, the statistical, so in order for us to say that this really is a new fundamental particle, this is a big thing to say. You can't, if there is a 2% chance that it's just a fluke, a statistical fluctuation that just looks like it, we won't claim anything. We need this probability that it could be something else to be much smaller than 1%. At the moment, the probability that this is just a statistical fluctuation is still a couple of percent. And it's like, if you know, while it doesn't sound like a large number, a couple of percent, it's really a dramatic conclusion to say there is a new particle. So we need to have a much smaller number. And this we can only achieve by taking even more data. And this is why even the newspapers were cautious in their announcements, saying this might be the first glimpse, this may be a hint, etc., because we only think this is a hint. We don't know for sure. What we know for sure is that the Higgs boson is not in many ranges that were allowed until early last year. So these plots I showed at the beginning, all the red is now excluded by our data, yeah? And in 2012, so we will take a factor 3 more data than last year. So together we then have a factor 4 data compared to what we have now. So instead of expecting 70 Higgs boson events, we would expect 280. And then we can be much more sure whether what we see is really true, or whether maybe it was just a statistical fluctuation. So let me then conclude. So it's really been more than 20 years that LHC has been designed and constructed, and it's, for me at least, well, the Higgs boson is also exciting, but it's also very exciting to just be taking data so we can finally do that science that the community has wanted to do for over 20 years. The LHC will definitely answer some and hopefully many of the fundamental questions that I alluded to. The first significant data set was really just taken in 2011, and the Higgs results were the very first results that that we made, which used the full data set. We're making a lot more physics results, of course. And we will take about 3 times more data this year in 2012. And so the Higgs mechanism was really first invented already in 1964, and the LHC might prove this theory correct within the next year. So if it really is there, then we should be able to make a definitive statement by the end of this year, within this year. It's very confusing to be in January of a year. So it can, of course, it's also possible that we exclude the presence of the Higgs boson, and this would then challenge the theorists a lot. Most likely now it looks like the mass value is now at 125 times the proton mass, and in fact the my theoretical colleagues are already trying to understand what are the exact implications of such a value. But this excess could still really be a statistical fluke with a probability of about 1%. There's a lot more, of course, ongoing. I could only give you a glimpse, and there's here some links to web pages for explanation, articles, movies. Also, I know that all the brochures I brought, they've already been taken, and some of you didn't manage to get any. There's all of this material is also available on the web. I'm sorry, I should have brought more. Okay, thanks, that's all. Oh, yes, lights. Questions? Yes?
So, during the talk, you said that Higgs might not be a fundamental particle, it might be a composite.
Right.
What are the implications there for mass, for what the fundamental particles might be, and so on?
So it wouldn't really change the particles that we have today. So when it's composite, so the most common theory is that it is composed of 2 W bosons, and then what would happen is that we would find new resonances, new particles that are mirror particles of this Higgs boson at very high energy. So we would not see this 125 GeV little thing, but rather instead we would see at masses of a factor 10 higher or something, we would then see a W boson pair production resulting from such particles. Yes. So this is a big thing. I mean, so this is really what we are, that either it's a fundamental scalar, this is the theory of the Higgs boson, and it's a fundamental scalar particle, scalar means spin 0, or it's a composite particle. And in both cases, there is a known experimental program how to address that. And that one takes longer, but by 2018 we should also know that. Yes?
Is it a theory that there's a Higgs boson for ordinary matter and a different one for dark matter, or would it be the same boson?
It's the same. Well, it's a bit tricky. So it's in principle the same. However, in the theory of dark matter, which is the theory of there's many theories, but the most preferred theory is supersymmetry, that dark matter is the lightest supersymmetric particle. Now, in supersymmetry, actually, there's not only one, but there's 5 Higgs bosons. That's, yeah, but yes.
You shared about the amusing analogy of Margaret Thatcher at the party to describe how the Higgs field has been mapped to particles. But how does that field explain different masses?
Well, it's, Margaret Thatcher, Brad Pitt, I don't know, who's more, some people may have different, you can be a minor celebrity, a very exciting celebrity. So that's, in that analogy, that's how one would imagine it. So first there comes maybe some B-movie star and people kind of cluster around that person, but then Brad Pitt comes and then he can move much more freely the other one. So this is basically, but of course we don't have an infinite number. We only have a total of 20 particles. Well, 16 really that it needs to give mass. So it interacts differently with each of the particles and then gives a different mass. But, yeah. Yes? Yeah?
It's not a given that the human mind can understand the universe.
That's right.
Wondering if you think the LHC can actually maybe provide an answer eventually.
It's baby steps, yeah, in research. It's really, we have to take each step at a time. That's such a big question altogether, whether we can fully understand the universe. For that, we need to, for instance, understand dark energy, which is really, the Nobel Prize was given here to one of our faculty members last year, but this is much more mysterious. This is really very simple compared to the understanding. The understanding here of the Higgs boson is excellent compared to the understanding of why there would be so much dark energy. So it is possible that we find something at the LHC that, so there are no theories even that tell us what we should look for at the LHC to shed light on dark energy. However, I cannot exclude that we find something bizarre that then spawns actually a lot of theoretical development, and somehow it happens that one gets a much more fundamental insight in a problem like that. It cannot be excluded. It's possible. Yeah, you can't. But I think the chances are not so good. I'm hoping that LHC can explain the origin of mass. It may well be able to explain dark matter, which would already be a good. It might explain antimatter matter. So explaining everything, I don't know. Yes?
Question number one, you said one of the doing the diagram of superchemistry, the shadow one.
Yes.
How do we know that the shadow?
Well, because we haven't found it yet. So the bigger in these diagrams means that it is more massive.
Right.
So if the superpartner, so in supersymmetry, each particle gets a superpartner. If the superpartner of the electron had the same mass as the electron, we would have already seen it 40 years ago. So we already know it's a symmetry. We call it a broken symmetry, which means that the partners don't have the same mass. So for instance, the other symmetry you know well is the charge symmetry. So matter and antimatter, those particles have the identical same mass. In supersymmetry, in that symmetry, this is not true. If that theory is correct, for sure the masses are different. This we know. Yeah. We have a whole bunch. We have 100 million protons on one side from the other side hitting each other, and only a very small fraction of those 100 billion hits each other, typically like 10. So typically when 100 billion come from each side, typically 10 to 15 of them interact with each other, and only one of them makes an interesting interaction. Yes? Oh, that's, so just the helium bottle, basically? Hydrogen bottle. And then we strip off the electrons in that sense. So it's very simple, actually, yes?
When you have the proton-proton interaction, and it's defined at 17 eV right now, the reaction energy that you're talking about is at 17 eV. That's with protons, it's at 3 parts.
Right.
So isn't it 1/3 of that?
Yeah, no, yeah, so in the very simple quark model, it would be 1/3, but actually I simplified a little bit. So even if it consisted of only 3 quarks, it's not that everyone has to carry exactly 1/3 of the momentum. It's a distribution. But typically, it's true that in these collisions, so we have never seen an event which actually made it all the way with 70 eV. So typically, it's about, I mean, with the valence quarks, which are these 3 quarks, it's about 10-20% of the energy. Now, it's even more complicated because the proton doesn't only consist of these 3 quarks, it also consists of a lot of gluons and further quarks, and so it can have an infinitely small momentum. So most interactions, they carry only less than 1/1000th of the proton momentum. But those, then they can't make the Higgs boson because they don't have enough energy. So, yes?
How do you relate this to classical physics segments? Can you derive from the field equation that this is the coefficient
No.
of inertia? And can you derive that this is the source of gravity?
No. So no, because it's not. It is unrelated to gravity. This is the confusing thing because it is not explaining how macroscopic masses interact with each other. It is solely explaining why any particle at the quantum level could have any mass at all. So it is not, so F equals ma, this Newton's laws, this is really explaining how masses get accelerated, yeah, and how forces act on masses. It doesn't, but but Newton does not explain why anything has mass, right? So here, this is completely. So it's impossible to relate. Yes. Yes. Yeah. Yeah, but it's in quantum physics because F equals ma doesn't even. I mean, this is really only for macroscopic particles. So we're dealing here, I said you at the beginning, the mass we're dealing is at 10 to the minus 30 and so on. And so gravity doesn't, gravitational interactions don't play a role. Yes? Yes. Yeah, so this is a bit confusing, right? Because we don't know if it exists, but then I tell you a lot of precise things about them. This is, yeah, so unfortunately I don't find it now. I think, no, it was the other one, right? Where I said it's 1% and 0.2%. This one. Yes, so this is what our theory, so we have a theory which has the Higgs boson fully incorporated. So we can actually, our theory knows everything about the Higgs boson. Now the theory might be wrong because it doesn't exist, the Higgs boson, but under the assumption that it exists, the theory can calculate anything. So it can tell me exactly, well, apart from that, the mass, yeah, but then we just, so this calculation here is for a certain mass. Here I just used 130. If the mass is different, in fact, these exact numbers are not correct, and it decay in some other way, but it fully predicts it. So we just insert, so the only free parameter that our theory has is the mass. So we just calculated for any mass it can possibly have between 100 and 600, and then it can tell us at any mass value what are these fractions. Yes?
Let's say you do find the Higgs boson, and then according to that little diagram you had, that was the last piece.
Yeah.
Standard model picture.
Yes. Are we done? Yes. Yeah, no, so this is, yeah, no, that's a good question, of course. I mean, so, yeah, so this standard model, I mean, it's really an amazingly successful theory. It has been developed. I mean, so the Higgs mechanism in '64, but really the whole theory was put together in the '70s. And since then, it's been tested and tested and tested very successfully. The only piece that's missing is the Higgs boson. It's missing experimentally. However, there are many other things that we think should have an explanation. So particle physics is trying to really understand what are all the fundamental particles that play any role in any phenomena that can be observed or that would have been present in the very early universe, yeah? And one of the things that we know from astrophysical data, from cosmology data, is that there is, and also from galaxy rotation, where it's absolutely 100% sure that there is dark matter in the universe. But our standard model doesn't explain that. So it is the last missing piece of the standard model, the Higgs boson, but we definitely know that the standard model is not a complete theory because it doesn't have dark matter in it. It doesn't explain where all the antimatter has gone. And these are really observed phenomena that we know of for sure. The number 3 is a bit more philosophical. I mean, it just may as well be weaker gravity. The theorists think there should be a good explanation. It shouldn't just happen by accident because you try to see if you can have a logical explanation that makes sense for everything. And so number 3 is also, so yes, for the standard model, it's the last missing piece, but what we really, and we call it like this, we say often we're looking for a lot of physics beyond the standard model. These would be supersymmetric particles that explain dark matter. So I didn't show all of this today because I didn't have time, and also we haven't seen anything in those yet, unfortunately, but it's still very early days, so. No, we're doing it in parallel. Remember, we have 3,000 people. So there's approximately 500 working on the Higgs boson such, and the others are working on all kinds of other things.
That's a good point to wrap up. And I hope to see you again on February 18th. But thanks for
See here these yellow dots. These are then the 4 experiments. So what happens at the Large Hadron Collider, you have protons colliding with each other in these 4 points. So one set of proton goes this way around, the other one goes counterclockwise, and then they are brought to collisions at these 4 interaction points, and which we have equipped then with large, what we call detectors, with large detectors. The one that I'm actually working on, and we have a large effort here in Berkeley on this, we have about a group of 45 people working here on the ATLAS experiment. And then the other experiment, which does very similar science, it's actually identical science to the ATLAS experiment, is on the opposite side, the CMS experiment, and I'll talk about those two. The other ones, called ALICE and LHCb, they are geared also at particle physics, but at different aspects of it, and I'll not talk about them. They don't do anything related to the Higgs boson, basically. LHCb is trying to understand antimatter, and ALICE is trying to understand very hot conditions in the early universe. So it's also very interesting. Just to give you a feel how big the LHC is, so I've transported it here into the bay, so it has a diameter approximately of the Bay Bridge. And remember, so the protons go around, one set goes clockwise, the other counterclockwise, and they go very, very fast. They're going at 99.999999% of the speed of light. And how fast that really is, what they do is they make a full turn around this ring 11,254 times a second, okay? And there's a lot of protons there. So in fact, we put them into bunches, these protons, and there are 100 billion protons in each bunch, and we have 1,000 bunches. So there's a lot of protons there. So how does the accelerator then actually work? So protons are, we are trying to get them to be at very high energy, and in order to do that, this is how, some of you, I think, might remember for the rest of the talk is mostly mass, but we don't really measure mass in kilograms or pounds or any of those units, but we use them as the unit of electron volt over c squared, where c is the speed of light. So I wanted to explain to you what that is. So 1 electron volt is equals to 10 to the minus 36 kilograms. So 36 zeros, 18. The particles that we're going to talk about, so protons are being accelerated in the LHC, so the mass of a proton is 1 giga-electron volt, which corresponds then to 2 times 10 to the minus 27 kilograms. The electron, for instance, which I think you're all familiar with, has a factor 1,000 smaller mass approximately. Just to set the scale, I also just put here the mass of the sun. That's 2 times 10 to the 30 kilograms. So basically the mass of a kilogram with respect to the sun is a very similar relationship to that of the mass of the electron. And the Higgs boson, which we'll talk about, of course, this has a mass which is about, which we don't know, as I'll say, but it should be in the range between 100 and 600 giga-electron volts. So it's about 100 to 600 times the proton mass. And this, of course, then again translates to of the order of 10 to the minus 25 kilograms. So when I talk about a heavy particle, this is very relative. I consider the Higgs boson to be a heavy particle, but of course, in terms of the masses that we physically deal with in daily lives, it's a very tiny mass. But it's heavy compared to, for instance, the electron or the proton. So the unit that I will mostly use is giga-electron volt. I try to always say it's equivalent to the proton mass, but sometimes I might slip into slang. So just remember, a giga-electron volt is just equals to the mass of the proton. And so at the LHC, we are trying to create very high energies. We are also succeeding with that. We are creating very high energies, and here I want to explain why this is actually important. So it really comes just down to Einstein's famous formula, E. Remember how TVs worked before they became all digital, or plasma TVs don't work like this, but TVs like in the 90s or 80s worked like this, that you have a radio frequency. Every time a proton passes, this radio frequency energy from the radio wave is transmitted to the beam, giving them a little bit of a kick. So they get just a little bit of a kick every time. They pass around many, many times, and that way they get more and more energy. And then they get more and more energy. Now, this is a picture of one of these devices. If they get more and more energy, then what protons like to do, normally they go just straight. So they just fly on straight forever. This we don't want. We have a circular machine, so we need them to go in a circle. And this we do via magnets. It's via the Lorentz force that we apply a magnetic field, and that way we can make them go around in circles. And these are very large magnets. So this is the Director General of CERN proudly presenting one of these large magnets. Yes? Sorry? Okay. 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 Okay, no problem. Thanks. Okay. Now, accelerators were actually first developed here in Berkeley. In fact, Ernest Lawrence, who was a faculty member in the physics department here in the 30s, he won the Nobel Prize in 1939 for the development of the first accelerator ever. And this is called the 5-inch cyclotron. The reason that it's called the 5-inch cyclotron is that it has a size of 5 inches, and it's displayed here at the left. The energy, and I'll explain these units in a moment, the energy that this 5-inch cyclotron reached was 80 kiloelectron volts. The LHC accelerator has an energy, reaches an energy 80 million times larger than that of Lorenz's cyclotron. It is a vast scale. You see here again the magnets. Here you actually see one of these. So there's 1,000 magnets of these 1,200. And this is when the last magnet was lowered into the LHC ring, which is also 300 feet underground, through these shafts, was lowered into the accelerator ring. The cost of it is, of course, also substantial. It's $8 billion. So the best way of explaining everything is to have a movie. So I'm having a movie now, which I hope works. Okay, so here we have a proton. So they start off at very low energy and then become into pre-accelerators. The booster, this is the so-called proton synchrotron. Then they go into the super proton synchrotron. You see these two bunches of protons going around, and now they're in the LHC. And so they're circulating, and then we are now diving into the LHC. Here you see an interesting formula, which I'll explain later. So we're going like this is the French-Swiss border you just saw. So this is a proton. It's a very dynamic object, which they tried to illustrate here, which has quarks inside. So now the proton here, one coming from the right, one coming from the left. Now this is the Atlas detector, and now they collide. And when they collide, then a lot of new particles get produced. And this is what you see here. And this is the essence of what we're trying to do. So a lot of new particles get produced, and we're trying to understand exactly what are these particles, to measure all the energies, everything about these particles that got produced, okay? So, and the particle that we're most interesting, and which particle gets produced is not predictable. Sometimes a Higgs boson can get produced, but much more often less interesting particles get produced. It's just purely a probabilistic thing. Whenever two protons collide, there is a probability that a Higgs boson comes out. There is a probability that other standard model particles come out. So we try to record all of them where we have some logic to filter out the most interesting events when we are already online when we're recording. So this is a slightly boring thing, but it's very important. So because so what we're going to talk about. Okay, thanks very much, Steve, for this nice introduction. I'm now going to turn off the lights, which is better for the filming. Is that okay with everyone? It also, you can see the slides better. You can't see me as well, but I don't think that matters. So let me talk I'm going to tell you about the Higgs boson at the Large Hadron Collider. This here is what we call an event display. It's a graphical display of one of the events that we recorded last year in the Atlas experiment at the LHC, and this may or may not be actually a Higgs boson. So, in fact, when I was first asked to give this talk, I was going to give a general talk, but mid-December, there were a lot of news stories, in fact, about the Large Hadron Collider, and here you see some from the BBC, which said that the LHC, the Higgs boson may have been glimpsed, and the New York Times said data hints at elusive particles, but the wait continues. So I'm going to tell you what this is all about, about these tentative hints for the Higgs boson that we may have seen last year. So the outline is that I'll first talk about the Large Hadron Collider, what it is, how it works, and what its experiments are and how those work. I will then tell you about the particle physics in general, what are the current successes of particle physics, and what are the remaining mysteries. And in particular, I'll focus here on the mystery, what is the origin of mass, which the Higgs boson is explaining. And then I will tell you about the first results from the Higgs on the search for the Higgs boson before I conclude. Okay. So this is an aerial view here of the Large Hadron Collider. It's located at the outskirts of Geneva, at the Swiss-French border, in fact. It has a circumference of 16.5 miles. It's this red ring here. And you see, for instance, here in the back, there is Mont Blanc, the highest mountain in Europe, which you can, in fact, see from the cafeteria at CERN, which is the laboratory, the European Laboratory for Particle Physics. Then you